Buenos dias, and thank you for coming. It's an honor to be here with my colleagues and friends in Temuco. I had the pleasure of being here 2 years ago, made many friends, and it's wonderful to see you all again. I have two messages today. One is about inspiring students, and the other is about trying to provide an optimal learning environment for students. And I will tell you that, to me, these are the biggest challenges for teaching in science and technology, engineering and mathematics. Some of our greatest challenges lie here. So let's do inspiration first. Why is it important to inspire your students? We live in a time of remarkable advances in science and engineering and technology, and we have to share the excitement of these advances with our students. The problem is that most students don't appreciate the magical things that they have all around them now. For example, smartphones and digital cameras and the internet. Just examples. There are many others. In biomedicine, astronomy, and so on, students today live in a much more wonderful world with exciting possibilities than I did when I was a student. And we need to communicate that to students. So let's take these examples first. We need to share the magic with them so that we can be inspired, they can be inspired, to make their own new discoveries. The transistor, the basis for all our electronic devices today, was invented the year that I was born, in 1947. This shows you, long time ago, this shows you William Shockley and John Bardeen and Walter Brattain, the three people at Bell Laboratories who invented the first transistor, the first semiconductor device. Today, you can put 3 billion transistors on a chip. This is Intel's, get this right. This is Intel's Itanium chip. 3 billion transistors, exquisite chemistry and physics and engineering in a little device that's the size of your fingernail. The digital, and by the way, I think I missed a point here. Yeah. Integrated circuits came along after the transistor, and they were pioneered by Jack Kilby at Texas Instruments and Robert Noyce and Jean Harney at Fairchild. And Walter Moore is known, of course, today as the person who led Fairchild and Intel into the modern age of integrated circuits. There were Nobel Prizes awarded for all these things. Shockley and Brattain and Bardeen received the Nobel Prize in 1956 for the invention of the transistor. Jack Kilby shared in the Nobel in the year 2000 in physics. Walter Moore did not receive a Nobel Prize, but he became famous for Moore's Law, which hypothesized that the number of transistors on a chip in a microprocessor would double every year and a half. And he only imagined that that would be true for a couple of years. It turns out to have been true for more than 40 years, approaching now 45 years. And the typical smartphone, which we carry around, now has between 60 and 70 billion transistors that you can hold in your hand. It's just stunning. 16 gigabytes of memory is about 64 gigabytes of transistors, 64 billion transistors, and there are 5 billion more on the processor itself. So they're incredible devices. Students don't appreciate what they carry around. So, digital cameras are the same way. Students take pictures day after day, put them on Facebook and so on. They are incredible developments of physics and chemistry and engineering. The sensors in all digital cameras are based on the charge-coupled device, or the CCD. Half of the Nobel Prize in Physics in 2009 went to William Boyle and George Smith for inventing the charge-coupled device, the CCD sensor. Whoops, getting ahead of myself. The internet. The internet, which improves our ability to communicate all over the world at the speed of light, is made possible by optical fibers. Half the Nobel Prize for physics in 2009 went to Charles Kao for the development of optical fiber technology. This incredible development makes it possible for me to write to my colleagues in Chile and for them to write me back in an instant, and makes possible all the things you've seen for the last 2 days with the incredible innovations in courses here at Temuco and of course at other universities. So we will turn from inspiration to how do you do the hard work. And I'm going to speak for a minute about how we transformed the introductory chemistry laboratory that we teach at the University of Virginia. The problem with our old curriculum was that the experiments in this introductory chemistry course, the first course that students see when they come to the university, was a cookbook-style laboratory course. There were detailed recipes that students followed for every single experiment. Students followed a step-by-step procedure, filled in the blanks on a report sheet, which I'll show you in a minute, and they had no input into the plan of the experiment. In fact, most students had no idea why the experiment was done the way it was. They simply followed the instructions, collected their data, and wrote it into reports like this one. Here's an example of our old laboratory reports. A pre-printed page with blanks to fill in, and the student didn't have to think a bit about what they were doing, simply be able to do the calculations. That course was taught at Virginia for many years by people who did real science, just like most of the other introductory chemistry laboratory courses in the United States, by scientists who did real science in their laboratories, but then they came to their laboratory course that they taught, and they expected students to do nothing more than this. They knew that students weren't really learning how to do science by doing that. We decided about 3.5 years ago that there was a better way. So the rationale for our approach is to take the traditional cookbook labs and throw them away. Cookbook labs don't encourage critical thinking. And what scientists do every day is critical thinking. What engineers do every day involves critical thinking. We knew there was growing interest in reforming courses like this, so we took the dive and we tried it ourselves. The real basis of science is inquiry, and we wanted to apply that to our course. What is inquiry? Inquiry's best definition, perhaps, is students drawing justifiable conclusions to answer a research question through the systematic analysis of data. It requires all those parts. And we set out to build that into the course that we were teaching. How did we do it? Well, first we looked at what had been done by others. There were a few other bits of research available about guided inquiry, project-based laboratory courses. And those bits of research told us that students in guided inquiry labs learn more than students in traditional labs. That had been documented. We knew that interactions with the teaching assistants were going to be very, very important in that course. We call them TAs, and from now on I'll just use the phrase TA from time to time, but you'll know that it means a teaching assistant. The beliefs and knowledge and prior experience of TAs are very important in a guided inquiry laboratory. So we will emphasize that and tell you a little bit about how we set out to improve the ability of the TAs to be good teachers in a guided inquiry format. First, I'll show you a quotation from Martin Schwartz at Yale University, and I hope you don't mind if I read this with you. One of the beautiful things about science is that it allows us to go along getting it wrong time after time and feel perfectly fine as long as we learn something each time. No doubt this can be difficult for students who are accustomed to getting the answers right. No doubt reasonable levels of confidence and emotional resilience help, But I think science education, scientific education, might do more to ease what is a very big transition from learning what other people once discovered to making your own discoveries. This is what science is about and what students need to learn. And then we translated that idea into a new laboratory manual for our course. And here's just one little quote from that new laboratory manual. And this is the first thing the students see when they get ready to start our laboratory course each fall. Chemistry can be challenging, especially when you are asked to act more like a scientist. Developing your own experiments and drawing conclusions from the data you gather rather than following the prescribed directions. You may not get the results you expected, and that's okay. This is how science works. We wanted students to be comfortable with the idea that they're not to get the right results, they are to analyze the results that they obtain. So our new curriculum is based on a project-based approach. Students are given a problem every 4 weeks with a driving question which they have to solve through research and the process of inquiry. In the guided inquiry model that we use now, students are given a specific question to solve, and they develop their own plan and their own procedure for answering that question. Students are provided with guiding questions, but then they have to develop their own procedure. So let's see how this works. Guided inquiry promotes good scientific practices. What do scientists do? They ask questions. They develop and use models. They plan and carry out investigations. They analyze and interpret data. They construct explanations. They engage in arguments from the evidence that they get, and they obtain and evaluate and communicate their results. They don't just fill in blanks on a page. So, it's going ahead. So our new curriculum, every semester, has 4 projects each semester, and students work in cooperative 4-person teams. We organize the teams on the very first day of the semester, and we try to distribute students so that we don't have all outstanding students in one group and weaker students in another. They are mixed by gender and by background and previous experience and so on. And then these 4-person teams work together through the semester. Each project involves 1 planning day, the first week is a planning week, then 1 or 2 days of experiment, and then a day for student presentations of their results. And in the end, they have to submit a lab report, which we'll talk about in a minute. Like so many of the stories that you've heard the last 2 days, we've replaced our lab lectures with online videos, a flipped laboratory, if you will. But we also know that TA training is important, so I'm going to say a few words about that too. Tell you a little bit about the students in our laboratory. We have more than 1,400 students who take our course every fall. It's a large crowd of students. And this turns out to be about 40% of the incoming students at the university each year. They all think they're going to medical school. and so, you know, that doesn't really happen for all of them, of course, but they all start out thinking that, so they all have to start out taking chemistry. And we have 24 students per laboratory section, so we have to have between 58 and 60 sections of students in the laboratory course each year. This requires a lot of teaching assistants and, of course, a lot of organizational effort. Tell you something about some of the projects that we assign to the students. We emphasize solving real-world problems. Now, you can't do very much with a first-year college student in terms of solving a real-world problem, but we've come pretty close with a couple of good ideas. First one, identify a white compound found at a crime scene. Well, of course, it's not really found at a crime scene, but that's just for them to think about. Determine the conditions and best practices for transport of solvents used in perfume manufacture. We looked at solvents that were used in the perfume industry, and we thought we could do some good experiments with liquids and vapors in a project like that. This one is relevant where we live in Virginia because we get a lot of ice on the roads every winter. So we challenged the students in one project in the winter, as a matter of fact, to develop an optimal de-icer compound for the roads and highways. And in that one, of course, they have to think about the ability to melt the ice, first of all, but also about the safety and transportability of whatever it is. They have to think about those things. The other project I'll mention here is developing a safe and effective liquid calcium supplement for elderly people. That involves, if you think about it, developing a solution that has a high enough concentration of calcium in solution and one that is safe and non-toxic for people to drink. No one really drinks these solutions, of course, but the students are challenged to develop something that presumably would be safe to drink. And each one of these projects is presented to the students in a single page that describes the problem and gives them a couple of guiding questions to help them solve it. So here's an example. This is the calcium supplement assignment. It's just one page, and you can see the description at the top. Many older people find they have become susceptible to osteoporosis, so they need to take calcium supplements. Most people would like to do this with a liquid, but they don't want to swallow something that doesn't taste good, and so on. So, criteria for completing the project. It has to be a clear solution. It can't be a suspension. It has to have a pH between 4 and 10, so it doesn't hurt the person who drinks it. It can't contain toxic materials. And it has a known concentration so that people will know exactly how much they're consuming when they take their supplement. And then the students are given guiding questions. And we don't have to go through these, but you can see there are a series of questions here that establish the rules of the project, if you will, and the things that the students should think about. But there is no procedure here. The students are not given a procedure to solve the problem. So what do? They work in groups. This is a picture of a couple of the teams of students in the laboratory. They have assigned roles. For each project, there's a team leader and a person who writes the plan for the experiment, and someone who writes the summaries each day in lab, collects the data and writes a simple summary to show to the teaching assistant. And finally, someone who manages assembling the equipment and disposing of waste appropriately. And we do take seriously the business of waste and toxic materials in a chemistry laboratory. These roles change from project to project. So through the semester, each student gets to be a team leader, or the plan writer, or the summary writer, or the equipment and waste manager. On planning day, the first day of the project, the students work together, each team works together to answer those planning questions and to develop a procedure for the following lab period. The team leader is responsible for getting the approval of the TA. The project can't go forward until the TA signs off on the project, literally signing the student's notebook to say, I approve of your plan. You're doing the right kinds of experiments. We have the equipment that you need for what you've proposed, and you're not using too much reagent, too much chemicals, and so on. The TA will only approve the plan if it has a good chance of accomplishing the project goals. That's the first day of each project. Now, to tell you how this develops through the semester, the very first project, the very first week of the semester, this is so unusual for students. As someone said in the previous talk, they've all come from 12 years of memorize and regurgitate and being passive learners. They don't know how to do this. They truly don't know how to sit down with a group and make a plan for a set of experiments. And we've actually had students start this for 20 minutes and run out of the lab and start to cry and say, I don't know how to plan. And it has happened. And we tell them, it's okay, come on back in. And by the second and third and fourth projects for the semester, they are experts. They have learned the procedure, they know what to expect, they know what things to think about, and their skills in planning improve every single project. It's impressive to watch. So, here's a close-up picture of some of the students developing their plan. They have to submit that to the TA and get approval. Then, during the experimental weeks, they have to keep notes in a research notebook that looks more like what you would see in a research lab than what you saw in the cookbook labs. Detailed notes of what solutions were used, what was done, step by step, and so on. And each day at the end of the experiments, the summary writer has to write a summary that describes everything that was done, the preliminary results, what to do next in the following week, and so on. Oops. Here's a picture from the laboratory. This is my colleague, by the way, Lindsay Wheeler, who some of you met last year when you came to Virginia. Lindsay working with two of our students, and she's acting here as the TA. Lindsay's moved up to be an instructor for our course now, but she has finished her PhD, and before that, she was the head teaching assistant for our course. So, very important differences between the cookbook and the guided inquiry labs. When the TA is in the lab, like Lindsay here, students will ask, how should I do such and such? What do I do? The TA is taught not to say that in our new labs, but in the old cookbook labs, they would say, well, do it this way, and then show the student exactly what to do. The student learns nothing, doesn't think critically. In the new guided inquiry labs, the TA's response to this question is, that's a very good question. Let's talk about it. What do you think, to the student? And you start a conversation, but you never give the answers to the students. You let the students develop the answers for themselves. They learn to think. They learn to go to the next step. In the fourth week of each project, the students present their work to their peers. The laboratory section is here. The presenters are up on the side that you can't see there. And they speak to the group and they present the results of their experiments. We have 24 students in a section. We have 4-person teams, so that means each presentation day there are 6 presentations. And one by one, the groups come up and they present the results. And every student in the section is required to ask one new question at least in each of the presentation days. So if you're in this section, during one of those 6 presentations, you have to ask a question that no one has asked before in the group. That means that the students pay close attention. We worried for a long time before we started this if students would be playing with their phones or doing email and Facebook while the other students were presenting. But they are so concerned with asking a unique question that's thoughtful that they pay very close attention. We never have to remind the students, pay attention to the presentation. They're very, very good about it. And it's one of the nice things about this whole process. The students who present are graded on the content of their presentation, on the visual aids they use, and their delivery. They have to be able to speak clearly. They have to be able to be heard in the room. And they have to be able to communicate effectively to their peers. This is new for most of them. Most first-year students at the university have never had the chance, never been required to speak about science to a group of people. So this is very new for them. And yet, they learn a lot as they go along. They get very good at it. The students' lab report is the last thing they have to do for each project. And we expect them to emulate an actual scientific manuscript. They should include an abstract, an introduction, an experimental section, results and discussion and conclusions, and of course, references. So we expect this of the students. We help the students prepare for the laboratory. Students have never done this sort of thing before. They need to learn the laboratory techniques, and they don't know most of the techniques they will use. So we want to emphasize critical thinking about the problem, but we also have to teach them the techniques. So all the techniques go on online videos, and we leave it to the students to watch the videos and learn the techniques before they come to lab to try them out. Some of the things we teach them in the videos are as simple as how to dress for lab. You can't come in shorts. You can't wear sandals. That would be dangerous. You have to be covered from your neck down, and of course, bring a lab coat. How to take good notes, how to make pH measurements, and so on. All of these are in the videos. We have actually more than 15 now. It's up over 20, and we keep adding new ones as we find new things for the students to do. But the teaching assistants are the most important part of this process for us. It's very important that the TAs know how to be a guided inquiry TA. We use both graduate students and undergraduates for these. Each TA supervises 24 students in a lab section. Oops. And in the lab, they guide the planning for each team. They approve the plans. They challenge students to think critically, ask them, what do your data mean? Oversee lab safety and act as facilitators, of course. Outside the lab, they hold office hours to answer student questions, and they grade the lab reports for each student in their section. So the TA training is so important that we spend a week before the semester starts every August doing training of our TAs. They think about and are guided in discussions about what is inquiry, what are their responsibilities. They actually do the first 2 student projects themselves in the lab as if they were the students, so they will know all the problems that might be encountered. They learn how to interact with students in the lab, how to do the grading, and of course, how to use the technology in the lab. It's a picture of TA Training Week. This is Lindsay working with a whole classroom full of TAs in August, the week before the semester starts. TA development through the semester is important as well. We hold weekly meetings with the TAs. We discuss the practical problems and issues with the experiments. We review the grading, discuss the scientific content of each project, and the TAs, of course, have to complete the other 2 student projects. And they're also encouraged to go to university seminars to learn about teaching and learning. We assess the TAs and the students in these labs. And without showing you the data, because you've seen lots of data already, I'll simply tell you that we see very positive changes in the TAs throughout the semester. Their content knowledge improves. They really start to understand inquiry, and they enrich their own beliefs about teaching. We've had several graduate students decide that they want to go into teaching after being our guided inquiry TAs, in fact. And they do pre and post training surveys and an end of semester survey and so on. We interview them each throughout the semester, and the instructors collect feedback as well. I'll show you just one comment from a TA that shows you what this has meant for them. It's easier for me to ask particular questions or dig deeper because I've seen students already go through it, and I know they're capable of understanding what the lab is asking, and I can push it further. I know they'll get it. But this is only after the TA has become confident in what they're doing. Is this effective? The student comments tell us that it is. We have an experiment at the start of the semester on glassware accuracy. Student says, planning was very difficult. This is just to measure the precision and accuracy of glassware, and it still was difficult. I've never done labs like this before, but planning was an overall enjoyable experience after the first lab because I saw the benefit of it. When a plan was successful, it was a great feeling. My TA was fantastic during planning. She facilitated critical thought in a nearly flawless way. Let's see, one more. I was surprised by how much I enjoyed the presentation. It wasn't very hard or stressful, and I definitely think it gave me a better understanding of our experiment and how it relates to the real world. And there's a comment here about student learning, but I'm going to go past that and tell you just this from a student. I was really glad to have taken this lab this year. By the end of the semester, the students changed from saying, this is much more difficult than the old labs, to saying, I really understand the benefits that I've gained from it. Now I want to thank the people that have worked with me here in Temuco. They have all been wonderful. You know them all, I think. Ricardo and Hector, Andrea and Beatrice and Hans. 3 years ago and some, I think in the spring of 2013, have I got that right? Something like that. Hector and Hans came to the University of Virginia and we first met, and that led to my coming down here. And I want to add just one thing about that. 2 years ago, we talked with the wonderful chemists that you have here, Nicholas and Aida, Maria Teresa, and Victoria, about how they could implement the same sorts of things here at Temuco. And they took those ideas and they ran with them. And you saw this morning the incredible results that Nicholas and Aida presented. They have just covered miles of progress in just 2 years. And I'm frankly amazed at what they've done. And I congratulate you on a wonderful, wonderful job here at Temuco. And it's, you know, these are the people that got it started. These are the people that made it possible. They were the liaisons that made this work. So, muchas gracias to everyone at the center. I couldn't find the color logo, so I had to steal one in black and white from the internet. Did the best I could. And I just want to say thank you, gracias, for your kind attention. And I would be happy to share information about our experiments with anyone who would like to write. There's my email, and I would be happy to do that. Thank you very much. Gracias.
¿Preguntas?
Hi, thank you very much for the presentation. I would like to know how do you deal with the individual advance of the students? If this is for the group, if the standard is of the course, I don't know. When we make inquiry, this is very difficult to control.
It's very difficult to control, and we mostly work individually with the students that find this difficult. You may find it interesting. I don't know how things are here in Chile exactly. I don't know your demographics. But now at the University of Virginia, we have more young women coming to college than young men. Our enrollment is about 58% female and only 42% male. And the young women are generally just fantastic. They have made such strides, and it's a great time to be a young woman in college. And you know, whatever limitations that any of the students face, we simply try to work with them individually. I should tell you too that we have students from many places that come to the university with very different backgrounds. And we have students from what we call Northern Virginia, near Washington, D.C., in what's called Fairfax County. And there's a school there called the Thomas Jefferson School for Science and Technology, I think. And those students have better lab equipment in their high school than we have at the university. They are very well off financially, and they know everything. I mean, they're very smart kids. On the other hand, we have students that come to us from the southwest part of Virginia, where they don't even have high school chemistry laboratories, and a bus comes around to the school about once a month. The chemistry bus comes to your school maybe once a month. And so those students are at a great disadvantage. So we have this incredible disparity of students. And I think that's much like what you face at Temuco. And so we have to really deal with each student individually. I hope that answers your question a little bit.
Sí, sucede que nosotros en los laboratorios de física muchas veces le planteamos a los alumnos un desafío. Y al trabajar en grupo uno ve que emerge un líder, una persona que se adelanta a los demás y empieza a proponer soluciones. Y uno ve que los demás le siguen. ¿Cómo maneja eso uno?
And I just know Hector's going to translate that
In
to me.
the physics lab, sometimes one student goes ahead under arrest and starts proposing solutions to the different problems and experimentations they are doing there. So how do you deal with that at Virginia?
That's a very good question. As I said, we try to split the students up so that there are not too many good students in one group. But each one of the groups works independently, and so they're isolated from each other. One group here, one group there, and so on. So even a star student here with good ideas for his or her group won't be influencing the others. That's one thing to separate them. But the other is that within a group, one of the jobs of the team leader and the TA is to gain a sense when one student is dominating the project. I have a son who was trained at Purdue University as an engineer, and he would tell me all the time, "Dad, we worked in groups, but one or two people contributed everything and the other two went to sleep and didn't do anything." And so we knew about that problem, and we tried to talk to the really outstanding students and say, "We know you get it, we know you understand this, but please give a chance to the other students to make their own contributions." It's part of the process all semester of trying to make sure that each student gets a contribution, and it's the job of the team leader to do that, and also of the TA. I hope that helps a little bit. I should add one thing about working in groups and solving problems together. We have a colleague at the University of Virginia, a physical chemist that some of you may know of, named Brooks Pate. And Brooks started his own chemical company a couple of years ago. And the way he always does things is very thorough. So he went out to companies all around the US and other continents even, and said, "Tell me how you run your business." And he learned from them for how to start his own business. And at the end of every interview with a company, he asked the same two questions. He said, "What do you expect out of new college graduates in science, and what do you see?" And he said the answer was almost universally the same. Companies would tell him, "Students have a lot of knowledge, they know a lot of things, but they can't do anything." And so he would say, "You put 5 students in a room, give them a problem, and they have no idea what to do with it." We're trying to change that. And here at Temuco, as you saw this morning with Nicholas and Aida, that's happening here too. And I think it's going to take a couple of years before you see the so-called fruits of your labor. But 5 years from now, 10 years from now, those students that you trained here in inquiry methods are going to be successful in their future work and their professions. And I think it's going to take a while to see it, but I think you'll be very proud of the results. Thanks.
Hola.
Hola.
Mi pregunta va un poco enfocado, porque yo me doy cuenta que esta metodología está más enfocada en el desarrollo del pensamiento científico más que en los contenidos, que me parece súper bien. Pero mi pregunta es, los alumnos que reprueban, por ejemplo, o los alumnos que aprueban, ¿cómo se mezcla con haber pasado cierto programa del curso?
We're still collecting data, and we ask the students to do this voluntarily, so we don't require them to be evaluated. We make it an individual option. We have to be careful not to require them to do that. But it's been successful as far as we can tell, because they go on to their later courses and do very much better in organic chemistry laboratory and so on. But even better, most of the students who take that, well, not most, many of the students who take that introductory course go into research laboratories in their second or third year, and they work in a real research setting, and they come back to us and say, "It helped so much to have the introductory course because I learned how to ask scientific questions and I learned how to look for solutions." We have some real data on that. Lindsay has it, and she's writing it up for publication, and I don't have the exact numbers here. But it's been very positive but mostly we hear back from the students that they really see that that laboratory course contributed to their critical thinking skills. They've never had to do it before when they come to the university, and they realize after taking our course that it made a big difference for them when they get into a research setting. Muchas gracias.